Okay, everyone, we are back to talk about oxidation reactions. So we just finished talking about reducing agents, and now we're going to talk about reagents you would use to do the opposite type of reaction. If you want to start with an alcohol and turn it into an aldehyde, a ketone, or a carboxylic acid. And you might want to take a minute and pause the video to make a little chart in your notes that looks like this. I'm going to talk about how different types of alcohols can be oxidized by different types of reagents. So in terms of alcohols, alcohols can exist as primary alcohols, which means that you have an OH where the oxygen is connected to a carbon that's connected to only one other carbon. You can have a secondary alcohol, so the alcohol is connected to a carbon that is connected to two other carbons. Or you could have a tertiary alcohol, like tert-butanol, where the OH is connected to a carbon that's connected to three other carbons. So traditionally, a lot of the oxidizing reagents that have been used in the past contain chromium. So chromic acid is your most common oxidizing agent. And that has the formula, let's say it here, we'll write chromic acid. Chromic acid is usually generated in situ in a reaction. Its formula is actually H2CrO4, but if you're running a reaction, usually we use sodium dichromate, Na2Cr2O7, and we use that under acidic conditions, so we put in some sulfuric acid. Or a lot of times in different textbooks or different published papers, you might see someone using a combination of CrO3 and acidic conditions, so H3O+, maybe that's sulfuric acid. But either way, either this combination of reagents or this first combination of reagents, when you mix them together, you generate chromic acid. So that is your oxidizing agent. Chromium is in a very high oxidation state, so it's a great oxidizing agent. In fact, this is what I would consider a strong oxidizing agent, and I'm not really sure where I'm gonna squeeze this word strong in here. These are my strong oxidizing agents. If I want a weaker version of an oxidizing agent, we'll list a couple options there. Now, chromium is toxic, we know that it's carcinogenic, so there are a lot of greener alternatives that exist and more that are being developed. One of the most common ones, which we will use in lab in our very last experiment, if we have time to do it, is to use NaOCl. This is just bleach or pool chloride. So that's also a very strong oxidizing agent, but it doesn't have that toxic chromium in it. Sometimes it doesn't give as good of a yield, so that's the trade-off. But either way, if you use one of these really strong oxidizing agents on a primary alcohol, you're going to take this carbon that has one bond to oxygen, and you're going to add on as many oxygens as you can. So in this particular case, or in any case with a primary alcohol, it'll go all the way up to 3 bonds to oxygen, which means that you turn your alcohol into a carboxylic acid. If you have a secondary alcohol that you're oxidizing, again, you're going to turn any hydrogens that are on this carbon are going to get removed, and you're going to add multiple bonds to oxygens. So in this case, there's only one hydrogen to take off. So the best we can do there is form a ketone. You can't break any carbon-carbon bonds, so you can't turn this one into a carboxylic acid. And then for the tertiary alcohol, this carbon doesn't have any hydrogens on it. There's nothing there to remove to make another bond to an oxygen. If I tried to make another bond to oxygen, I would have 5 bonds to carbon, and that can't exist. So there's going to be no reaction when you try and oxidize a tertiary alcohol. It's just impossible to oxidize them. Now, in the case of weaker oxidizing agents, you can sometimes stop the reaction from going as far as we showed there. So a weaker oxidizing agent would be something like PCC. This one contains chromium, and I'm not going to write the whole formula up here. I just want you to be aware that it is not a nice, safe oxidizing agent. It also contains chromium, just like our chromic acid. It's just a different form of chromium, so it ends up being a weaker oxidizing agent. But we abbreviate it PCC based on what its full name is, and if you want to look up the structure of that in your textbook, you can. If you want to do a greener version of this, greener means that it's more environmentally friendly. Then you might do something called the Swern oxidation. So you can just write Swern oxidation over your reaction arrow, or you could do something called a Des-Martin oxidation. These are named after people who discovered them. So you can write either of those over your reaction arrow. And again, if you want to look in your textbook and see what the combination of reagents is to do these reactions, you can. But the main result of these is that in the case of primary alcohols, because these are milder oxidizing agents or weaker oxidizing agents, you actually only oxidize the primary alcohol up to an aldehyde. That's the main thing here, is it stops at the aldehyde. Stops at aldehyde. Okay, so if you want to make a carboxylic acid, you go for your strong oxidizing agents. If you want to make only an aldehyde, then you go for your weaker oxidizing agents. For secondary and tertiary alcohols, you get the same result because there never was a chance for a carboxylic acid to form in the first place. So secondary alcohols, again, give ketones, and tertiary alcohols, again, give no reaction. There's no proton there to pull off. So really the main difference to keep in mind is with the primary alcohols. Depending on what stage of the oxidation you want to stop at, you have to be careful about which reagent you choose. Okay, so that is our grid of all the different oxidizing agents that you might encounter. Now, all of these oxidizing agents basically follow the same sort of mechanism. So I'll show you the general mechanism, and I'll show you an example, maybe with the first two here, just so you get the idea of how this works. It's an unusual mechanism, the way it makes the carbon-oxygen double bond. We've never seen one like this before. So let's clear our board and write out that mechanism. Nice and clean. Okay, so the mechanism for oxidation follows this pattern. So the first thing that always happens is that something attaches to the oxygen that is a good leaving group. So when we're writing out this mechanism, we're going to attach a good leaving group to the oxygen. Okay, the oxygen itself is not part of the leaving group. We're just attaching something onto it that is itself a good leaving group. So we're basically replacing the proton that's on an oxygen with a good leaving group. And then there's going to be this little step where the best base present which is usually water, especially under acidic conditions, it's going to be water. It pulls a hydrogen off of the same carbon the oxygen is attached to. And this will make more sense when I draw the picture in a minute. But then what happens is an E2-like reaction occurs. So we'll say, and an E2-like reaction occurs as the leaving group. This leaving group that we originally attached, as that leaving group leaves. And you're going to notice when I draw a picture of this that it really does, it looks a lot like an E2 type of mechanism right at the end. Okay, so that's the general idea, and I'm going to show you an example, one or two examples of this happening. So, let's see. We'll do this with chromic acid first. So Chromic acid is your basic, strong, traditional oxidizing agent. Let's say we'll just do this with a secondary alcohol. So the first series of steps to add the chromic acid, here's chromic acid, like that. There are lots of protonation and deprotonation steps, tons of them. As this oxygen attacks the chromium, things kick up, kick down, protons come on and off. So there are a bunch of steps there that eventually end up in this chromium being attached to the oxygen. And the main thing that all oxidation steps have in common is that this is a great leaving group. Notice I didn't circle the oxygen, okay? This is not like this is not like an SN2 reaction where you're trying to get the oxygen to leave. The oxygen's going to stay on here. It's everything attached to the oxygen that's a good leaving group. And so then if I follow what I had written before is what happens. We had said that the proton attached to the same carbon as the oxygen. Okay, so I'm going to draw out that proton. That proton there then gets pulled off by the best base present. And in this case, if you're in acidic conditions with chromic acid, your best base is going to be water. So water is going to act as a base. It's going to pull off this proton. And then we're supposed to treat this as if it were like an E2 reaction. So in an E2 reaction, the base pulls off the proton. This pair of electrons forms a pi bond. So that's how we're making our carbonyl compound. And then our good leaving group leaves. So these two electrons go with the chromium and they leave. And that's it. Now we have a double bond to an oxygen here. But we have never seen a double bond form to an oxygen in this way. So this is a new style of mechanism that you just have to get used to. Let's do the same thing with bleach, with NaOCl. You're asked to do this as one of the post-lab questions in your very last lab. So write it down now and then copy it later. So same idea. The only difference when you have bleach is that what ends up happening after a couple steps is that we then have an oxygen with a chlorine on it. And so the chlorine is now the great leaving group. Good leaving group. And so the same last step is going to happen. My best base, which is probably water, is going to pull off the proton attached to that carbon, the same carbon that the oxygen's on. It's going to kick over and make a double bond, and it's going to kick out the good leaving group. And I'm going to end up here, I'll just draw my arrow here, I'm going to end up with the same exact molecule, because I use the same one to start with. Okay, so that's the mechanism for oxidation. It's the same general mechanism. The only difference in every type of oxidizing reagent is that you'd have a different type of leaving group attached to your oxygen. So this is a good time for you to pause the video and try problems number 4 and then number 5 on your worksheet. So I'm going to clear the board as you do that. And then when you think you've gotten the answers, check back in with the video because right now I'm going to go over problem number 4. So problem number 4 on our worksheet says predict the product in each reaction shown below. Okay, so we just have to know what these different oxidizing reagents do. The main thing is to be able to decide if it's a strong or a weak oxidizing agent. So in A, we're using PCC. What you have to do in this reaction is to recognize that as a mild oxidizing agent or a weak oxidizing agent, and to realize that it's only going to oxidize primary alcohols to the aldehyde stage. So notice here I have a primary alcohol. Over here, I don't really care what kind of oxidizing agent I have because it's a secondary alcohol. So that's going to become a ketone. But over here, instead of turning this all the way to a carboxylic acid, it's going to stop at the aldehyde stage. So my final product here is this becomes an aldehyde. If you want to draw out the hydrogen, you can. I often do. And that becomes a ketone. Okay, but important to know that it's only an aldehyde, not a carboxylic acid. In my second example, in letter B, we're using a combination of sodium dichromate, Na2Cr2O7, and sulfuric acid. That's how we make chromic acid. I have a primary alcohol on this side, and I have a tertiary alcohol over here. Tertiary alcohols, there's no proton to pull off there, so I cannot oxidize that alcohol. But the primary alcohol with a really strong oxidizing agent, that will get oxidized all the way to the carboxylic acid. And then nothing happens to our tertiary alcohol. So there's my final product in letter B. Okay, if you haven't done number 5 yet, maybe pause the video again, take a few minutes and see if you can figure out number 5. We're now incorporating oxidation and reduction reactions into our synthesis problems. So while you do that, I'm going to erase my screen here and get set up for number 5. Okay, so in number 5, we're asked to convert this tertiary bromide into an aldehyde. So I'm not changing the number of carbons in my molecule. It looks like I still have a 5-carbon ring and then a carbon here, 5-member ring and a carbon here. So I don't have to make any new carbon-carbon bonds. But it does look like I need to move my functional group over from this carbon over to this carbon. And I need to turn it into an aldehyde. And since we've just been talking a lot about oxidation reactions, if we think backwards, retrosynthetically, if we can get this to be an alcohol, then I've just learned about a whole bunch of different oxidizing reagents that I can use to try and oxidize that into an aldehyde. So if I want to make an alcohol there, this is tertiary. So this looks like a good candidate for doing some sort of elimination reaction maybe. And if I want to make sure that I get an elimination, not a substitution, I want to make sure that I don't do an E1 reaction. An E2 reaction would be my best bet. It's tertiary, so I know that it's not going to compete with an SN2 reaction. In addition, I want my double bond to end up between these 2 carbons. I don't want it to be the more substituted double bond, which means that I'm trying to make a Hoffman product. So in that case, my best choice is to use a strong bulky base, maybe sodium terbutoxide, maybe DBU, whatever your favorite strong bulky base is. But that will put a double bond on the outside of the ring. And then I want to add water across the double bond. I want to do a hydration reaction so that I get an OH adding across this double bond. And I want my OH to end up in the anti-Markovnikov, anti-Markovnikov position. And we do have a reaction for doing that. We're going to use hydroboration, BH3THF, and oxidize that off with H2O2 under basic conditions. So that will give me the anti-Markovnikov hydration product. And that's what we were trying to get to. That was in our retrosynthetic analysis. And then finally, I just have to pick the correct oxidizing agent to use here. Sometimes you have more than one choice, just like you had more than one choice for a bulky base. In this case, it's a primary alcohol, and I only want it to turn into an aldehyde, not a carboxylic acid. And so that means I have to be careful and use one of those milder oxidizing agents. So you could use PCC, or you could use the Swern oxidation, or you could use a Des-Martin oxidation, whichever is your favorite mild oxidizing agent. You can write there over the arrow. Okay, so that would be it. 1, 2, 3 steps. This is a good stopping point for this video.